Hi friends, this is EL4501 Unit 3 IC Fabrication by Dr. M.R. Gadhvi. In today's lecture, we will be focusing on photolithography. Photolithography is one of the process of a monolithic IC fabrication, and this is a word basically made up of two different part of the terminology. One is a photo, which is related to light and visible light especially. Litho, that is a stone, and graphy, that means the science. So on a stone you are carving something science with the technique of a photo. So that is what the literary meaning of the photolithography. With the photolithography, it is possible to produce a microscopic small circuit patterns on a silicon wafer. So basically it is the process which is the very important and major part during this process, and where we are going to develop the small circuit on the IC chip, or a chip, or the area which is reserved for a single IC. The whatever the processes you are going to execute for a one IC, naturally you will be going to execute for the all available number of IC on the same wafer, and therefore rather than doing the same circuit many times, there should be some photographic technique should be developed, and therefore on each segment of the IC it should be engraved or it should be taken shape, and therefore the photo technique is important over here. To execute such thing on a certain region of a IC chip, a certain component going to be executed. माने कि थोड़े आईसी के छोटे छोटे आईसी, पहली बात तो ये है कि वेफर का बहुत सारा चिप में सेपरेशन किया, रादर द स्केलिंग किया, एंड वो रीजन जो डिफाइन किया ईच आईसी चिप का, वही आईसी चिप पे वी आर गोइंग टू डेवलप द different circuit with the help of the allowed fabricated component, that is either gates or the transistor. We know that number of transistor will decides the size of the density of a IC, and let us say here we have mentioned the 10,000 transistors, so it would be the category of a LSI, large scale IC, and that IC would be run from 1 mm to 10 mm. It is a conventional process using a UV light, and UV light having a wavelength around 2 micrometer. If I do have a 2 micrometers, and then it is allowed to pass the very small mask which is made up of a glass, and therefore there is a possibility of a diffraction, and henceforth there is a lateral separation, lateral development of the IC fabrication, which is not allowed. So in kind of a minuses of a fabrication. To overrule this minuses, we do having a very basic fundamental logic. If I want to reduce the diffraction effect because of the mask which is going to be used in the photo technique, then I should choose the smaller wavelength than the UV. UV has a wavelength some around 2 micrometers. The X-ray is a much smaller than that, about 1 angstrom, and electron beam is even further smaller than the X-ray, around 0.3 microns. So that way, if you want to do some carving or development or a circuitry part on a sub-micron range, then UV is not the ideal tool, but X-ray or the E-beam is the ideal tool for mask and photolithography. If UV is not going to be used, it won't be tagged as photolithography, but it would be rather tagged as a X-ray lithography or the E-beam lithography, which is I mentioned here. Anyway, now this photolithography having a, in principle there is a two part. Keep one thing in your mind that this two processes having also सब processes. तो बार बार यही चीज़ आएगी कि हर एक कोई प्रोसेस में there is a sequences of further processes, and that's why in a IC fabrication, to get a perfect shape IC you have to work a hell number of steps of the processes and more than 100 hours of job on a one piece of IC, or rather one wafer. And second, so the first process is designing of the mask, and second one is the photo etching. Etching, that means to notching out from the any particular. Okay, so designing of the mask, which is the first part of the one of the process of photolithography, designing of a mask. So mask is basically, in principle, it is made up of a glass, and that glass having a alternative dark, that is opaque, and transparent or a clear region. And along with this preparation of a mask, it is too difficult to work out at a sub-micron level or even at a micron level size to designing of a mask, and therefore a photography technique is exploited over here. Some around 500 times zooming is going to be executed, and zoom effect will allow us, let us say I do have a size of my IC is 50 mils by 50 mils. So if I will do a 500 time magnification, the range of some around 60 centimeter by 60 centimeter, it's a huge. Even manual handmade variations you can execute it on that, and from that particular development, with the help of a photography technique, you further again reduce to your desired size or lesser than micron, and you can enhance the density of the component. The further part of a designing of a mask will allow us that initial layout is decomposed into a several mask layer, and each corresponding to a process steps in a fabrication, as for example a mask for a base diffusion, the another for the collector diffusion, and another for a metallization. That means in nutshell हर कोई एक प्रोसेस के लिए एक अलग तरीके का मास्क बनाना पड़ेगा. वो काफ़ी अंडरस्टैंडेबल चीज़ है, क्योंकि अगर मैं ट्रांजिस्टर का मैं 3 हिस्सा बना रहा हूँ, तो अगर मैं पहले कलेक्टर बना रहा हूँ तो कलेक्टर की साइज़ विल बी डिफरेंट, तो मेरी मास्क की साइज़ विल बी डिफरेंट. उसके बाद मैं बेस बना रहा हूँ, तो आपको पता है कि बेस वॉज वेरी थिन, वेरी मच थिन, सम अराउंड 10th part of the collector, and therefore it is a very thin one. So that should be the collector mask can't be used in case of a fabrication of the base, and that is what mentioned here, the base diffusion mask, the another collector diffusion mask, and all another processes having the another masks. Okay, so the here artwork is not any a line diagram, but it is a alternate clear and transparent and opaque regions. So mask is basically a artwork, there is no doubt about it, and basically it's made up of a glass and sequences of a clear transparent or opaque regions. A widely used material for a glass material or photographic film material is known as a clear mylar. I know that because I had work on it, and this is mylar is very well known, made by the DuPont company. You can search it on your Google as well. So once the clear mylar coating is exposed under the UV light, then it becomes the opaque and very much solidified. So clear mylar is a very thick gel shape material, but once it exposed under the UV light, it becomes the opaque layer. The artwork is usually made on precision with the very nice mechanical device which is known as a coordinatograph. Coordinatograph is a very pin type pencil holder having a 2-dimension x and y dimension variations, and both these axes are perpendicular to each other. So that is known as a coordinatograph. I repeat, the mask is designed on a glass with a photographic technique with the enlargement, and to design a particular circuit, the variations on a mask designing are carried out by a tool which is known as a coordinatograph. The individual ruby lith pattern is photographed and reduced to 5 to 10 times. अब ये जो हमने पैटर्न बनाई है इन लार्ज रीजन में, उसको फिर से फोटोग्राफिक टेक्निक यूज़ करके you are going to reduce it, and one has to develop the negative, and this negative will be useful in the next process. Final image is also repeated many times on the matrix array on the IC chip, and therefore at the same time many number of IC will be developed in the same batch. Finally, a uniform deposition of a photoresistive emulsion. As I said, a clear mylar material is going to be deposited. It is also known as a photoresistive emulsion or a photoresistive material on the wafer. Basically, a Kodak photoresistive material, as I have given the example in a photography room or in any showroom, you will be finding out the laminated photograph, and this lamination is nothing but the clear mylar, or nowadays a commercially well known as a Kodak product and so on. And this is going to be exposed under the UV light. A pictorial diagram of our book is given like this. I do have a silicon wafer. The red layer is referred as a silicon oxide. So when you are going to oxide in a tabular furnace, I think we had already discussed a multi inlet tabular furnace having a possibility to connect it with different gases. And on top of the silicon wafer, we are going to deposit a photoresistive film, and this photoresistive film is basically going to protect the silicon oxide. This silicon oxide is protecting our silicon wafer, and the photoresistive material job is, as for the mask designing, you having a chance to etching out the different region of the silicon oxide, and you can remove them as per your need, and you can create an island on a wafer, and each island will be going to use to fabricate a different component, and these components will be further interlinked. So here you can look at here, this silicon SiO2 layer is deposited on by SiO2, and this SiO2 is deposited by a very uniform photoresistive material, and this photoresistive material is capped with the mask, and mask is made up of, you look at here, a dark and transparent and dark and transparent region, and this entire sandwich you are going to expose under the UV radiations. Wherever there is a dark material, the photoresistive material beneath of that is not going to be solidified because the UV light is not reaching there. But wherever there is a clear mask or a transparent mask, the UV light will transmit it through the glass or mask, and therefore this region is going to be solidified. So the dark mask region of a photoresistive material is still in the gel shape or a not unsolidified region, which is you can remove it, then you can touch the SiO2 or silicon oxide layer, and when you will be going to touch that one, so naturally you can further do the process on wafer itself. The UV exposure solidified the photoresistive material due to polymerization beneath a transparent region. If you look at here, why it becomes solidified? So basically, mylar is a material, it is a monomer, and when it is exposed to a UV light, it becomes activated and it become the it get chance to get polymerized, and polymerized that means it gets solidified. The second part of a photolithography technique is a photo etching. In the photo etching, we are expected to removal of a SiO2 or the silicon oxide layer. So we can remove only those SiO2 layer which is beneath the dark region of a mask. माने ट्रांसपेरेंट रीजन मास्क के नीचे तो यूवी लाइट पहुंच गई तो वो फोटो रेजिस्टिव मटेरियल या तो माइलर है वो सॉलिडिफाइड हो जाएगा, इट इज हैविंग अ गुड एडेशन विद द SiO2, तो वो नहीं निकलेगा. लेकिन डार्क रीजन ऑफ अ मास्क के नीचे जो फोटो रेजिस्टिव मटेरियल है वो जमा नहीं होगा, सो वो इजीली निकल सकता है. But once it get removed, then you can having a chance to etch out the SiO2 layer. Now sometime SiO2 layer can be easily etched out and sometime it is not, therefore you need to clean that one and you require a certain chemical, and in general it is also known as a etchant because it is help us to etch out the SiO2 layer. This all are your small questions. Which material is going to be used for the etching or as an etchant? So then you can write it out. A trichloride hyaline is one of the best solvent for removal of the extra unsolidified photoresistive material, and the certain chemical called the etchant is like a hydrofluoric acid or a formic acid will be used to remove the SiO2, and sulfuric acid also is very well known and many times used to removal of a photoresistive material and the additional impurity. So in nutshell, in a photo etching process, our prime job is to remove the SiO2 layer. The SiO2 layer from the wafer can be easily removed by a certain chemical, and that is known as a trichloride hyaline. Rather, trichloride hyaline, which is dissolve the unexposed or unpolarized photoresistive material. So पहले photoresistive material निकालना पड़ेगा, उसके बाद यहाँ पे पिक्चर में थोड़ा क्लियरली दिख सकते हैं. सो दिस इज़ unsolidified photoresistive material, so which is removed by the trichloride hyaline. तो ये solidified है because ये ट्रांसपेरेंट रीजन के नीचे था, ये भी ट्रांसपेरेंट रीजन के नीचे था और ये डार्क रीजन के नीचे था. तो ये जो यहाँ ऐसे ही मटेरियल दैट इज़ अ माइलर मटेरियल या तो फोटोरेजिस्टिव मटेरियल था, दैट इज़ रिमूव्ड बाय trichloride hyaline. Once this is removed, you require to clean this up, and then you have to need to remove the SiO2 material also. And to remove the SiO2, we can use the hydrofluoric acid or a formic acid. It is widely used in the industries. The sulfuric acid is also very well known to remove the polymerized photoresistive material, because once I able to success the removal of the silicon wafer, I am say SiO2 layer on a silicon wafer, it is the job is almost done for the next set of processes. The photo etching is also called the wet etching, rather the removal of a trichloride hyaline or a hydrofluoric acid or formic acid or a sulfuric acid. So these all are basically etched, and when this all are the solutions and the hot water treatment are given to the chip for removal of a SiO2 and photoresistive material respectively, the sets of processes are known as a wet etching. In the advance, there is also known as a dry etching, where there is no chemical will be used and just a removal of the unwanted thing by plasma etching. As I told you, the processes of SiO2 exposure, UV light, and passing of the different gases, so it is through the tabular furnace, and this all are the sets of processes. So let us say here the photolithography. Within photolithography, again these three things are repeatedly occurs. To formation of a mask also we need the epitic oxidation, and the dark and transparent region will be going to be developed with a photography technique, and thereafter before diffusion is going to be start, you should be in the shape of such way, that means the silicon wafer is open up, and therefore only the diffusion will takes place. So here this silicon wafer I am able to create a p type diffusion, or I am able to create the n type of a diffusion on it. So how it is possible the diffusion, we will see again in the next slides. As I told in beginning, there is a one minuses using a UV light, that UV light having a wavelength of a 2 micron. So when it will pass through the mask, there is a possibility of a diffraction, and therefore there is a lateral expansion is observed in case of the ICs, island fabrication and so on. I will show you the picture so it will get more clear. But to overcome this lateral spreading of the island, and therefore once it gets spreading, it is too difficult to control the parameter of the IC. So let us say this is the way to get solidified of a photoresistive material when it exposed to UV light. तो ये region dark बन जाएगा, ये रीजन भी डार्क बन जाएगा, लेकिन ये जो ब्लैक के नीचे है वो डार्क नहीं रहेगा. सो यू कैन रिमूव विद द सल्फ्यूरिक एसिड, सॉरी हाइड्रोफ्लोरिक एसिड और द formic acid and so on. And with the advantage of X-ray and electron beam lithography technique, it is possible to produce a device even up to a sub-micron range, because the wavelength of the using tool is very small. In nutshell, the upper limit of a IC device, that is a density, may be enhanced. However, the X-ray or a electron beam equipment are very costly, and therefore there is an enhancement of a price if it is a X-ray lithography or the electron beam lithography is used on the IC. Okay, now the isolation technique. The isolation technique is very important in the fabrication processes, because one island, let us say you are preparing a one transistor, it should be 100% isolated compared to the next island component. Let us say second component में एक दूसरा island है, then the island 1 and island 2 should be 100% isolated. So that technique is one of the technique what we have to discuss. An isolation technique can be developed by a two-way. One is p-n junction diffusion and second one is the ion implantation. So let us start with the p-n junction diffusion. If you look at here, this is the what I had talked in the previous slide also. This is called the lateral expansion. So when a mask is going to be kept on top of the silicon oxide, because of diffraction, because the dark and transparent region of a mask looks like a slit, and therefore the diffraction can take place. Once the diffraction will take place, so I wanted to make straight, but it will get bent. So that is the reason number one. Secondly, there is a different concentration of a p substrate level and n substrate level. So there is an expansion of p-n junctions which is taken shape on this arc. Ideally it should be straight, but because of the potential well difference it get expanded, and in addition to that the diffractions of a UV light also make it that wedge is not right angle but a little bit widen up. So these all are the issues are overruled by using the small micron wavelength, and that is done by the X-ray beam or the electron beam lithography. Okay, over here we are discussing about the p-n junction diffusion. I told you require the furnace frequently, and see you should do the process at a 1000 centigrade, and 1000 centigrade either you need to make it a p-type material or you need to make a n-type material. Then for a pentavalent impurity you may having a phosphorus pentoxide or the phosphorus oxychloride, and these are the pentavalent impurity, whereas the barium chloride and the boron oxide, boron chloride and boron oxides are well known for the trivalent material. Trivalent impurity is going to be used. Sometime for the safer side, as I have shown you the tubular furnace with multiple inkjet of the gases, such kind of a tubular furnace used with the oxygen or the nitrogen. It is required for the sweeping diffusion, which is normally extended to 2 hours. This could be your one of your viva. What is the extended time period for the p-n junction diffusion technique? The answer may be different hours. You have to pick up the correct one, that is a 2 hours. I can ask you what are the trivalent impurity are going to be used in the p-n junction diffusions. So the boron chloride or the boron oxides is well known example. Similarly, the pentavalent impurities are the phosphorus pentoxide and phosphorus oxychloride and so on. Okay, so this is the isolation technique. If you look at here, island 1, island 2, island 3 and island 4, this diffusion is developed and all are separated by very equally p-type diffusion channel. The higher little bit diffusion channel is insisted because the separation of the potential well between the n epitaxial layer and the wedge p plus channel should not be extend too much high, and therefore it should remain as rectangular as it is expected, and there is a reduction in the less lateral spreading. So this is one of the reason. on an average it is observed if I do have a p type of material of substrate, if I want to make it, the concentration of the p type material is some around 1.4 10 to the power 14 atoms per centimeter cube, whereas in general all the impurities, or rather the silicon impurity and the dopant impurity is decided with the idea of 5 into 10 to the power 20 atoms per centimeter cube. So here the impurity ratio is quite different, quite high, and therefore it is shown by the P plus channel. If someone asks you that what is the reason to having a P plus channel, why the fabricators are insisting to having a P plus channel, the idea is only the island should not be laterally widened up. If it is get widened up, the calculation of the transistor or diode will be too difficult, and therefore it is always advisable. So this is an overview or top view or the bird view, where the surrounded cage is of a P plus channel and each island is independent to each other. So you can easily grow the component on each one. Okay, so this is again the main lateral spreading. This is a tangential view, and the earlier one was the bird view diagram of the isolation technique. Ion implantation. So in case of another methodology of isolation technique, that is the ion implantation. The ion implantation technique is the so thorough and so important technique that the lateral spreading through ionization implantation is almost like a nil possibility, or hardly 1% can be lateral spreading can be observed. The ion implantation is the other technique to introduce the impurity in the silicon. Impurity, that means the dopant. So in the process of a wafer are kept in a vacuum chamber, and it's scanned by the high energy dopant ion. This is a setup for the ionization implantation. This orange vertical long one is a it is a wafer holder. So you can see the black one on the left edge. Many wafers are sticked here, and this bar is rotating continuously in a forward direction, and this is a source of ion, and with the help of battery it got the mass separation electromagnet will diverted into the direction of the screen, and the accelerator will make a job of accelerization of this one, and this is a y deflections is observed, and you can control by the x diffraction. X deflection can be controlled by the another pair of a plate, and finally the beam of the electron, or rather the ion, will be reaching to the our needy target, and over here it is the many wafers together and so on. So anyway, so the process of a wafer are kept in your vacuum chamber and second and scanned by the high energy dopant ion. These ions are accelerated by energies of some around 20 kV to 250 kilowatt, and because of this is to having the very high energy and high requirement of IC, the local IC could not be using the ion implantation because it becomes the very costly one. Okay, ion penetrating depth may be controlled by the accelerating field. So as the acceleration electrons are very much controlled one, then the impact on a wafer and ejecting into the wafer on a particular layers, and that would be the way to do the ion implantation technique. And the depth of penetration is decide by your accelerating voltage, and the skin depth which is developed by the ion to be imparted. Okay, in the last discussion, the ionization carried out at low temperature, and this is the tendency for a lesser lateral spreading. And since your temperature is very much low, so naturally the silicon wafer will responding less, and therefore the lateral spreading will become less, as I told, because of a potential heat difference. The depletion layer will take the separations of the depletion layer, but you need to control over here, and that is good possible by ionization carried out at a low temperature, and thus the lesser tendency to form the lateral spreading. In this process, the accelerating potential and the beam currents are electrically controlled from outside, and this is the key advantage over here, that the acceleration of the potential beam, or rather the tool which is going to be imparted, which is controlled from the outside. And if I compare this technique with the diffusion earlier technique, then it is very highly sensitive to the temperature. So if the temperature is high, your reaction rate and everything will be affected, whereas over here it is quite focused. Thank you so much for paying attention. Stay home, stay safe.